All right, welcome back. This is lecture 9 of CS164, and after today we only have 2 lectures left. So next week we'll have our guest lecture on Windows Mobile and things related there too from a friend of ours, Edward Guarin from Microsoft. The week after we'll talk about issues of security, and then that's it. And then the few weeks after that we'll regroup after in the midst of you're working on and finishing up Project 3 for the SES Design Fair. So this is going to be a new thing this year, modeled in the spirit of the CS50 Fair, but meant to be inclusive of a whole bunch of classes, taking up multiple floors in Maxwell Dworkin. So more details on those in a few weeks, but the idea is that we'll have 1 or more time slots during that day. It's the first Tuesday during reading period. And the goal will just be to exhibit the projects that you guys and other classes have done this semester, particularly the choice of student projects. So more details via email. Today's meant to be a conversation about scalability. So especially when you're taking software courses in school, it's a little easy to get in the habit of just being handed things like an appliance or an account on a Linux server. And when you then finish up a course like this or some other course, it's not necessarily always clear how you can go about actually using those skills in some other environment. And particularly if your goal is to support some large number of users, to spin off some startup of your own, you yourself are going to have to figure out, do you buy a server, do you rent a server, what are the technologies you need to choose from, because obviously you'll no longer be handed a PDF that tells you what to do. So today is really meant to be a conversation and a design discussion about the kinds of larger scale issues you might have to decide on besides just the PHP framework, besides just the mobile platform you're choosing. How do you actually scale server side to support increasingly networked services? So with that said, suppose that you are trying to make an iOS app at this point in the term, or a few weeks back, a web application that needs to talk to some server. So Abel Hangman does not need to talk back to some central server, but maybe Project 3, your student's choice, will need to have some kind of server interactions, and certainly a web-based application, mobile or not, needs to talk to some server. So you finish up this course in a few weeks. Suppose you graduate college, you want to go start some company, or you want to go work for some software type company, and the goal is to have a web server. How do you go about procuring a web server so you can write your PHPs and your Pythons and Ruby somewhere on the internet? Literally, what do you do? Yeah?
Buy a VPS from a web host.
Okay, good. So there's this notion of a VPS. Some of you who took 50 might have recall some of these details or read up on them toward the end of that semester. So a VPS, virtual private server, what does that actually mean? What's a VPS? Yeah, Carl.
So they have like a bunch of boxes in some like farm somewhere.
Okay.
And then they just rent you out like space inside those boxes.
Okay, yeah, so there's some commercial vendor who, him or herself, actually owns a bunch of servers, and typically using virtualization software like VMware or something similar to VirtualBox, but for a server environment, chops up that hardware into the illusion of multiple servers, and then rents to someone like Carl the illusion of an actual server, a virtual server, in that Carl would have root access on it, an administrator account, he could install anything he wants on that server, but there are some gotchas. If you're using a VPS and you're paying someone $20, $50, $100 a month for a VPS, what do you need to beware based on that definition? Sounds great, right? Yeah.
There's other people on the same physical hardware.
Yeah, so there's other people on the same physical hardware, and it's certainly in the commercial entities' commercial interest to perhaps oversell their resources. So if they have, for instance, a 4-core machine, effectively 4 CPUs inside of the machine, it might be reasonable to slice that machine up using virtualization software into 4 virtual servers, each one of which gets a dedicated CPU. But suppose that one or more of the customers on that box really aren't that active, or their websites aren't that popular or that successful, don't get much traffic. So, it might be reasonable to run 5 virtual servers on that 4-core machine, or 8 virtual servers on that 4-core machine. And using virtualization software, you can still multi-thread things in such a way that everyone gets an equal fraction of the CPU. It's not a problem that you're sharing 4 CPUs over more than 4 virtual servers, but the implication is that suppose that one of these people gets their website linked on Reddit or Slashdot or something like that, and all of a sudden they get tens of thousands of hits one day. Well, what does it mean for the n-1 other customers on there? Right, they too might suffer. So there is perhaps a dependency there, even though the price tag of $20, $50 a month might be much more attractive than a $6,000, $3,000 physical server. So what else is there to be mindful of with a VPS, or what are alternatives to it?
You'll probably have to pay extra for a dedicated IP. So you'll have
Good.
to pay extra for SSL or something like that.
Okay, good. So you often have to pay a few dollars more a month for special services like a dedicated IP. And you pretty much addressed why you might want a dedicated IP. SSL effectively requires that you have a unique IP address because of the encryption involved. And long story short, if the data is encrypted, the server can't figure out whose website you've requested until the HTTP request has been decrypted. But if you don't know who the request was for on a multi-host system, you don't know whose encryption key to use. However, if you have a dedicated IP address for a site, you can just assume blindly that anything coming in on 1.2.3.4 is for CNN.com or whatever the company actually is. So for SSL, you have to pay a bit more. Other qualms or alternatives altogether? Yeah?
You might not actually use all the resources that you buy.
Okay, so you might not use all the resources you buy, or that you'd be buying, right? You might get some number of terabytes of traffic per month, which you don't really need. You might get some number of gigabytes of storage space, more RAM than you actually need. So in fact, there are more cost-effective solutions than a VPS, and most VPSs start, around the $50 per month mark. And if it's any less than that, you need to then start questioning, frankly, who the vendor is and to what extent they're oversubscribing. But you can have a more generic web host, right? And this is what cloud.cs50.net was in CS50 for those who took it when we had the cloud. And it's the one server, effectively. And everyone doesn't have the illusion of a machine on it. What does everyone have on a web host?
A directory.
So a directory. You have a home directory. You have a username and password. And that gives you the ability to actually host your content on someone else's server. But the downsides there include what? Yeah. You don't control the server, right? If you actually want some new Python library installed or PHP module installed or MySQL upgraded, you have to email the system administrators and ask if they will do that for you. And typically they won't because you are not the only one on that machine. And doing something for you could be to the detriment of other people who might be relying on certain versions or might certainly not want to deal with the headaches of upgrades. So commercial hosts often do trail in terms of the versions that you're using, and certainly you have less flexibility. So a common question toward the end of a semester is what web hosts could we use, should we use? This frankly is very much a religious thing, and you can ask a dozen people and get a dozen different answers. In 50 at least, this was a recurring theme when we asked people who do you use, who do you like. These are some names that you're welcome to Google. We've used some of these ourselves, and then in the VPS realm, these are some of the more popular folks. But if you're really kind of itching to learn more about system administration and running your own servers, actually signing up for a VPS or just running your own VM on campus, and you can request of Hewitt a dedicated IP address. If you own a desktop and you want to be able to connect to your own dorm room from some laptop on the internet, you can make that happen. Realize that at least playing with a VM, whether running on your hardware or someone else's, is a nice way to experiment. And Linode and a couple of these others are actually fairly cheap, but I wouldn't necessarily start a company using those, but it's nice if you just need an external server for whatever purposes. So if you need a server, you start Googling around for things like this, but unfortunately this only goes so far, right? Suppose that your website becomes quite popular, and so your one web hosting account doesn't suffice, or your one VPS doesn't suffice. So what are your alternatives? Suppose you very happily are getting successful and getting thousands of hits now per minute or per second even. Yeah, okay, so you have a bigger fish out there. So you have Amazon Web Services, AWS, and they have one service called EC2, Elastic Compute Cloud. And this is a more genericized version of this, whereby you don't have to go to a website, fill out a form, wait for a human to actually provision, so to speak, your VPS by actually clicking some buttons or running some commands. Rather, Amazon is really a self-service VPS architecture. And so simply by logging in to Amazon's website and by associating a credit card with your account, you can literally click a couple buttons yourself and within seconds have one VPS up and running, have 10 VPSs up and running, have 100 VPSs up and running, and then with a simple click can you shut all of those down. In fact, a few years ago when Amazon first released EC2, one of the neatest stories in the newspaper that I found was a story by a fellow at the New York Times who had like gigabytes worth of TIFF images, TIFF, of old newspaper articles from the New York Times, and they needed to digitize, well, they had already digitized these things by scanning them, but they, I think, needed to do something like OCR en masse on all of these things. And they had the software, but they didn't really have the hardware. And to do this efficiently would have required dozens and dozens of servers to be configured, to be powered on, to be connected to a network. And then after his project was done, they didn't really have a compelling need to keep a few dozen or whatever it was, 100 servers around. And so around this time, EC2 was getting popular. So this fellow spent a few days writing some software that would iteratively briefly, go through all of the images, digitize them, or do whatever he needed to do, and then quit. But then what he did was leverage EC2 and spawned, I think, 100 or so EC2 instances, and within 24 hours had digitized dozens of years worth of content, powered it down, and it cost a few tens, a couple $100 instead of literally tens of thousands of dollars. And so things like EC2 really let you scale not just for one-time projects, but also elastically. And this is the buzzword that Amazon has popularized, whereby if your normal steady state is to get a few hundred, few thousand users per day, but once in a while you might get slashdotted or posted on Reddit or something that draws a whole bunch of attention to you suddenly, not only can you go into Amazon's site, spawn a few more machines, and if you've prepared in advance, run duplicates of your web servers in the so-called cloud, you can then do that all automatically. You can set thresholds whereby if Amazon detects that you've crossed some number of users per second, you can have these machines even spawn themselves, duplicating the servers that you actually have so as to handle the load, and then when things quiet down, they power themselves off. And this is really actually quite exciting because the alternative up until just a few years ago was a place that looked a little something like this. So co-location refers to actually buying hardware and then storing it in someone else's warehouse. You could certainly store it in your own warehouse, but there's economies of scale of putting your servers in the same facility that already has cooling, already has power, already has lots of network traffic, already has 24-hour staff to deal with problems that might arise. And so just a few years ago, starting a company, certainly in anything web or software related that needed to scale, meant you would spend tens or hundreds of thousands of dollars up front, rack the servers in a facility like this, though they don't quite look as beautiful as this hallway here, and then you start running your business. And of course, if you have too much capacity, you've overspent, and if you're unexpectedly popular but you don't have the hardware, it doesn't take seconds to actually buy hardware, have it delivered, install it, configure it, to then scale up. So this is what's really compelling about the cloud. So cloud is kind of one of the most overused buzzwords these days, and really the cloud just refers to outsourcing your software or your hardware to someone else, but it's this immediate scalability and this elasticity that's been popularized by folks like Amazon that's made it really an exciting place, especially for people starting companies who might on day one need one server, but in a month, a happy month ahead, need 100 servers. You can do that much more easily and pay marginally for it, not huge upfront fixed costs. The gotcha is that some costs can add up. So besides paying for CPU cycles with something like Amazon, what are other computing resources that a smart business person might want to charge you for? Yeah. So memory, so the amount of RAM you're allocating. Indeed, that's one of the metrics by which Amazon bills you. You decide in advance how much RAM you want, rather than they don't bill you per usage per se. What other resources? Yeah?
If you're running processes on your code from behind it.
So running processes on your code, so actually using the CPU cycles? OK. All right. So in Amazon's model, no. So you don't pay for every CPU cycle that you're consuming. You essentially pay for a gigahertz machine or a 1.5 gigahertz machine. And if it sits there idly doing nothing, they still bill you. Whereas if you, and you can't go beyond that. You would have to provision more machines. But besides RAM and CPU cycles, so bandwidth is actually a big one. In fact, a few years ago when for some of my extension and then CS50 course, we started podcasting things, making them publicly available as open courseware, we actually used DreamHost initially. And we signed up for like a $19 per month account, which was amazing. And it gave us like a terabyte or 2 terabytes of traffic per month. The problem is when you're distributing 500 megabyte or 400 megabyte videos and you have many people downloading them, you can tear through a terabyte or 2 pretty quickly. And so our approach to scalability about 6 years ago was to sign up for a second DreamHost account and then a third DreamHost account. And then every time we exhausted our quota for bandwidth, we would just change the IP address to the other account, to the other account. And this was incredibly manual, but it also suggests how expensive this could have gotten if they had been charging us more competitive rates. That didn't work out so well. And indeed now we brought everything back on campus because Harvard has much more capacity and we don't pay for it directly than we would if we were using a commercial web host. What's another resource that you might consume when scaling upward? Yeah? Yeah, so hard disk space is another one. So with these VPSs, with these shared web hosts, you get some number of gigabytes typically. And frankly, that's often quite enough unless what you're really doing is collecting a huge amount of data. If you are a video site, if you are a photo site. But if you're just using MySQL, storing user data, and even logging lots of stuff, text compresses fairly well. So that's a little less worrisome, but another resource to be mindful of. So Amazon charges you for all of these things, typically pennies on the dollar, but it's something that adds up. So if you're actually curious about this, do have some enterprise in mind. If you Google for Amazon calculator or Amazon Web Services calculator, you can plug in some placeholder numbers like I expect 1,000 hits, I need this much RAM, this many CPU cycles, and they'll estimate what your bill might be. All right, so let's now start solving the problem, irrespective of who's hosting our servers, of scaling in general. So there's this notion of load balancing, which thus far, in this class certainly, we haven't had to deal with. Back in our web programming days, you had one appliance and thus one server, and you had as many clients as you had browser windows open. But this is not necessarily the most scalable approach, because as soon as you start having hundreds or thousands of users visiting your site, even per second, one web server might not actually be able to handle them all. How many hits per second can a typical web server handle from users? Any guesses? Just order of magnitude? The answer definitely depends, but how many zeros are we talking here? Any guesses?
Thousands?
Thousands. OK, so thousands is pretty encompassing. So thousands is a good answer. So you can expect a typical server that has maybe 4 cores or 8 cores, maybe a couple of gigs of RAM, and it doesn't really matter how much disk space. You can assume that it can handle maybe 3,000 hits per second, 2,000, 5,000. Any more than that, then you probably need some slightly fancier hardware. And I say it depends because it, of course, depends what your code's doing. If you have lots and lots of nested loops and things that consume cycles, obviously it will scale less well than that. But that's a reasonable starting point. A couple thousand or a few thousand hits per second. So suppose you get more popular than this and you actually have 5,000 hits per second. Or you have just a couple thousand hits per second, but your code is actually pretty involved. It's doing a lot of analytics. It's storing a lot of data. So each individual server can only maybe handle 500 hits per second. What do you actually do? Suppose you exhausted the resources of cloud.cs50.net or your own appliance. How do you start to scale up so as to handle even more users? Load balancing is going to be the answer. But how? What does this mean? Zach?
Add more machines to the problem and then
OK.
send users to whichever machine is the most good.
OK, good. So if this is a web-based site and we have a web server already, either in the form of the appliance or assume that your web server is now hosted on some physical box or some virtual private server, well, if you've got twice as many users, just double the number of web servers that you have. So your picture, you might have multiple clients as depicted up here at the top. You might have n servers down at the bottom. So you need some way, some device, some piece of software, generically called a load balancer, to figure out what client should go to which of these servers. Now, how do you go about doing that? How could we implement this black box, this rectangle of the load balancer? And let's just assume, for simplicity, HTTP for now. So user at home sits down at client computer, types in yourwebsite.com, hits enter. What happens? How does that request make it to server 1, 2, or ... n? Yeah? OK, good. So we could keep track of how busy each server is. And how do you want to measure busyness?
How many requests is processing at the same time?
OK, so let's keep track of how many requests each of these servers on the bottom of the picture is getting per unit of time. And whoever has the fewest at this instant will receive the next incoming request. So that seems nice and logical. Takes into account load. So you would think that you would have pretty uniform distribution, not of numbers of users, but of load across servers. So let's now ask the more technical question, how do you go about implementing that? Yeah, Kevin.
Do you maybe measure some objective measurable, maybe processing? I guess CPU usage or memory, and then distribute based on.
Oh, yeah, so absolutely. So if we didn't want to keep track of a specific number of connections, which might not reflect how much work each connection involves on the server, we could instead look at the more generic load. So how many CPU, what percentage of the CPU is actually being consumed right now? How much RAM is actually in use among those several servers and then just pick the lowest. That could work as well. So how does suppose that we now have software that someone else wrote that can answer questions of the form, who is the least busy? Or to whom should I send this request? Now let's ask the technical question of how do you route the request from client to server? What does this load balancer actually do? And again, assume the internet, so assume IP, TCP, UDP, whatever you're familiar with. How do you implement this? Yeah.
I would notify the client of the IP address of the server he needs to connect with.
OK, good. So if this is all over the internet, we're using TCP/IP, and the way that machines talk with TCP/IP is to address their requests to specific destination IP addresses. Why don't we just tell the client directly the IP address of whichever server is currently the least busy? So we need to involve the DNS system for this, right? Domain name system, so that when a client user at a client types in yourwebsite.com. Recall that in the story that you might have that we told in 50, that you might have heard in CS143, there's a DNS server somewhere at the ISP, at the university, whoever's closest to the client that answers queries of the form, what is the IP address of your company.com? So that DNS server could somehow be part of this picture and simply answer that question based on the current load. So that's actually nice. Works well in that it does indeed tell the client to then contact that specific IP address. So now let's find fault with this design. Yeah?
Well, computers cache DNS addresses as well as hardware. It's pretty bad about refreshing DNS.
Exactly. So caching, which generally is a good thing in that it can improve performance, it's also a bad thing in that information gets stale. And in this case, the information that might get stale is who is the least busy at this moment in time. And if you have browsers like Chrome and IE caching DNS lookups, which they do, and you have Windows and Mac OS and Linux caching DNS lookups, which they also do, and you have ISPs, DNS servers caching lookups as they do, even if it's for some number of seconds or minutes, the load on these servers is presumably going to be fluctuating quite a bit. And yet if we're answering queries based on this moment in time, and those answers are then reused for some number of seconds or minutes, we might accidentally end up overwhelming server 1 or server 2, and now we might actually have some users experiencing downtime or significant delays, even if server N is completely idle and has resources to spare. So DNS works. It's nice and simple. And in fact, we can do it even more simply with DNS. With DNS, we don't really even need a load balancer per se. We could just have the DNS servers use something called round robin, which in computing generally means not using any kind of intelligence to decide what answer to return, but just responding in round robin order. The first time I, the DNS server, am asked, what's the IP address of your company.com, I say 1. And then the next time I'm asked, I say 2. And the next time, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So round robin is actually quite nice and appealing because of its simplicity. But what does it suffer from as well? Sorry?
Stale information.
Stale, not so much stale, because it's not taking any information to account. So what's really the downside?
I was thinking, like, what if one of the machines goes down and it has a fault?
OK, good. So if a server goes down and you're still spitting out one IP address, 1/nth of your users might reach dead ends. What else?
You could have like asymmetric load per user. So like that first connection could be using a lot of resources. So by the time it gets back, you actually don't want to go back to server 1. You want to skip over to server 2.
Exactly. So if the first user that visits your website is really resource hungry and starts uploading lots of photos, whereas users 2 and 3 just check their wall real fast and then log off, well, you might be sending accidentally a disproportionate amount of load, not number of connections, to the same server. So it doesn't take into account load, but it's super easy, and you don't need to buy or configure special software to do it. You can do it entirely with your ISP's DNS setting. So upsides, downsides. So this load balancer then, we want requests to come in. How else could we do this then? If DNS doesn't seem to be solving this for us very reliably. Yeah, Dan?
Just the router, and it just routes the packets to the computer.
Yeah, so we could actually have the load balancer perform a routing function whereby the requests just come into the load balancer. Everywhere on the internet, the load balancer itself represents the IP address of this website, yourcompany.com. And when the request comes in, it's the load balancer who's closest to servers 1 through n that decides, oh, server 3 is now the quietest. Let me route this request to him. And then using lower level TCP mechanisms or Ethernet mechanisms can send that data from the load balancer directly to the server. The server will then reply to the load balancer most likely, and then the load balancer in turn will respond to the client. So not unlike NAT, network address translation, that your home routers might very well be using. And you can even be fancier than that. The load balancer technically could route the request to server 3, but change the return address to actually be that of the original to do direct return, as it's called, so that you do have to have this funnel of information all coming in. But if the data you're spitting out is large chunks of data, like video files, you don't need to pass all of those video files back through the load balancer. They can go potentially directly back to the user. Yeah, Meryl.
Is the load balancer synchronizing like databases or other resources stored on all these individual servers, or is there some way that it's intelligently saying, okay, you know, the client wants to use something on server 2, so we need to send it to server 2. But how do you aggregate databases and resources across them with this system?
Perfect segue. So short answer is no. The load balancer doesn't do any of that. And for those following along on camera, what does the load balancer not do? It doesn't take into account any kind of shared state that must be shared across these several servers. By shared state, we might mean sessions. So recall from PHP, there's the notion of the session superglobal, in which you can store stateful information, even though HTTP itself is stateless. You might have actual records in a database that need to persist across servers. Because again, in the round robin form, if I visit the website now, I might end up on server 1. If I hit reload or click on some link, I might end up on server 2 or 3 just by nature of my DNS lookup expiring, my getting a new IP address back. Or the load balancer itself might be dispatching me here at first, then here, based on changing load. But the problem is if these web servers aren't all identical, I could get very different views of the world based on chance, based on which server I end up at. And in fact, Facebook has not always gotten this right. Probably all of you at some point have logged in and you see some posts on your news feed. And then if you hit reload, you kind of see different ones. Even though they're not newer per se, you just didn't see them before. Hit reload again and you might see another view of the news feed. And this happens from time to time. And as best I can tell, it's actually just a bug, or it's something related to caching, whereby in each request you're getting an answer from a different cache, which is probably not the intended effect, but you can infer from these symptoms what might be going on. So how do we solve this? Ideally, we minimally want sticky sessions, which means that when you've created a session, and sessions generally remember that you have logged in or who has logged in, you'd like this information to be invariant across all of the servers to which you might be routed. So let's take a step back to PHP at least, but the same idea exists in Java and JSPs and Python and Ruby and web context. How are sessions implemented, say in PHP, since that's what we used?
The HTTP headers?
Yeah, so in the HTTP headers is what?
Sorry?
In the HTTP headers is what?
Is the user's login information, and then you can save additional session data in the database.
Okay, good. So, and it's not quite the user's login information per se. When I do go to CS164.net and I log in, and the website thereafter remembers that I've logged in, it's not going to be my username and definitely not my password that's transmitted again and again to remind the server that I've logged in, but what is passed in those headers? A cookie. So some fairly large pseudo-random value that was planted in my browser, in RAM or on disk by the server, and that server has another copy of that number, probably in a database, or frankly on a lot of servers just in /temp in a file called 1234.txt or some equivalent of that. And then inside of that file or inside of that database is the stuff that I want to be remembered about me, what my username is, what my password is, or at least an encryption thereof, what my phone number, email address, and all of that information is. So that is to say, once you log into a website, your hand, so to speak, gets stamped, and the browser, according to HTTP, is just supposed to remind the server with every HTTP request, I've been here before, I've been here before. And that number informs the server that I've been here before. So there's an obvious security threat here, more on that in a couple of weeks, and that if someone looks at or sniffs wirelessly your hand stamp, they can pretend to be you, and you've probably seen or heard of this. Firesheep is the fun story to tell in that context, or the software to play with. But in more applicable terms here, this cookie is problematic because where is this cookie information stored typically? Database or file system. If it's stored in the file system, which is the default for PHP, sessions are literally stored in /temp or in /var/lib/php/session or something like that. Well, what's the implication? Well, when I log in and I happen to be on server 1, I'm authenticated on server 1. But as soon as I go to server 2, my browser is still going to present the hand stamp, the big cookie value, but what is server 2 going to do with it? It's nothing, right? It's going to be confused. It's just not going to recognize that number. Or worst case, it's going to be a number that was given to someone else, but probabilistically that's not going to happen. But most likely case, he just doesn't have any session state for me. So what happens to me as the user? I'm prompted to log in again. So I log in again. Another cookie is planted on my computer. Then I get redirected back to the home page. This time the load balancer sends me to server 3. What happens? I'm prompted to log in again, right? So this just does not work very well. So how do we solve this? Storing cookies on disk seems to be bad, at least at first glance.
You can use signed requests.
Signed requests, OK.
So that way, you given the information on a cookie, you look it up against some database on the server.
OK, good. So if we introduce into this picture, actually in the signing isn't strictly necessary. If we introduce into the picture just a database, if the problem in this story is that /temp is unique to every machine, or /var, lib, sessions, whatever, is unique to each machine, well then clearly we need to have some kind of storage mechanism that transcends the individual servers. So you can actually use MySQL to store sessions, and every row stores some key value pair, and you can configure this in php.ini, which is the config file for PHP, and it kind of works just out of the box. But now follow the play devil's advocate here. What's bad about this solution? If we just add a database to the previous picture. Yeah, RJ.
If one database can't handle all the connections, that doesn't work anymore.
Yeah, exactly. If we were solving this problem of horizontal scaling, as it's called, when you duplicate your servers in this sort of linear side-by-side fashion, well, if the problem that we were trying to solve is scalability, and our solution now to the new problem that reared its head, that of the need for sticky sessions, is to introduce a central database, well, this is kind of a step backwards, right? We've scaled the web front end, but the database back end now is still consolidated in one machine. So what's going to be a solution there? Not just have one database, but have multiple databases. But now we need to balance the load on the databases. And so the picture starts to get a little messy. So we'll come back to this story. Thankfully, databases can, in fact, scale a little more readily than us doing it manually with load balancing. What would be another solution to this problem? Suppose you can't have a database. And suppose you don't know how to set up a database, so you got to come up with something else. Or you can't afford a database. Any number of constraints could exist here. What else could you do if the problem at hand is that /temp is unique per server? Yeah.
Just share a place in your file system.
All right. So, right, some of you probably have like file servers in your dorm rooms or at home, which is just a hard drive that's somehow shared on the network so that multiple people can access it. That feels like what we kind of need here, right? Why don't we just introduce a server into the picture, or use one of the servers and have him share his /temp directory or some other directory to all of the other servers? This would seem to solve the problem. You can use technologies like NFS, Network File System, AFS in the Mac world, and there's a whole bunch of protocols that allow you to share file systems across the network. Feels nice. I don't have to know anything about MongoDB or MySQL or any databases, but downside? Yeah.
Are we against centralizing data in a single server?
Damn it, right? So it's kind of the same problem again. A different type of solution, but really with the same end result. We now are centralizing our hardware with just one single file server. So one, that thing itself might not scale very well. But at least, if rather than have to do all of our computation, the only thing this server is doing is serving files, maybe one file server actually does get us a little farther in the story. So it can handle 10,000 users, whereas an individual web server might only handle 1,000. But there's also this theme in scaling of single points of failure, which frankly kind of means what it says, right? Like if that server dies, you're kind of screwed. Everything is down then. Even if you have 10 actual servers, if they can't share sessions, this means no user is going to be able to log in because your site can't remember that he or she has in fact logged in. So it doesn't seem like we've really solved this all that readily. So let's come back to that in the context of databases, where we will at least have some solutions. But let's also talk about how we can make better use of the hardware we already have. So let's shelve that. We have a whole bunch of solutions. They're imperfect, but we'll come back to actually solve that a little better. But caching, we mentioned along the way, is actually kind of a good thing. So what does it mean to cache, just in general? Or what is a cache? Sorry? What's a cache? What's caching? Yeah.
Copy files in RAM or in memory so that you can access them faster than on disk.
OK, good. So it's a copy of files in RAM or on disk so that you can access them more quickly. So what kinds of things might you want to cache when implementing a web-based architecture? What's that?
The output of a server-side script.
OK, so the output of server-side scripts, right? So something like Facebook is actually a pretty good example, even though as the years pass, it's getting more and more dynamic. But just a couple years ago, when you visited your own profile page, it was pretty much static. It might have changed a few moments ago, but it's not going to change automatically, as is the case now with nice little AJAX features pushing more and more news feeds to your page. So assume that a couple years ago, at least, your profile page might be more read-heavy or write-heavy. Which is the more likely scenario? Any arguments in one direction or the other? So it's probably more read-heavy, unless you're completely obsessed with updating your own profile page or posting to your own wall or equivalent. Odds are for every change you make or for every comment someone makes, probably at least 2 other people look or care to see that information. So it's reasonable, at least for a typical user, that it's more read-heavy than write-heavy. Unfortunately, generating that page might have to talk to a whole bunch of tables or even a whole bunch of databases to generate all of the HTML that has your list of friends and that has your list of family, that has all of your recent wall posts, has birthdays, have comments you made. It might be spread around a whole bunch of different tables, which is to say it might take a bunch of CPU cycles and time to gather all of that information. And it would kind of suck to have to do that again and again every time one of your friends visits your profile page. So as Yellis proposes, why not do all of that expensive work once? And what's the output? It's HTML. But rather than just send the HTML directly to the browser, why don't you yourself save a copy of that HTML in a string, store it somewhere locally in RAM, or heck, even in the file system in a .html file, so that so long as I don't update my profile and another 10 users visit it, all I have to do is grab that file from disk or from RAM and spit out the exact same thing again and again and again. And I can even do that with AJAX, right? I can at least spit out 99% of the page and then do a marginal amount of more work to just get the most recent comments to insert at the top. So Craigslist has actually popularized this idea, and you actually still even see the HTML files. If we go to Craigslist.org, and let's choose Boston, and we can choose, let's see, how about apartment housing? So let's pick random one. Let's see, gorgeous 2-bedroom, granite counters, newly renovated. All right. Not the nicest backyard. All right. So the relevant part here, though, is the URL. It ends in HTML, which frankly is completely meaningless. This can be simulated, certainly these days, but odds are it actually is an HTML file. And HTML files on a file system are actually pretty compelling for performance, because we've had like 20 years of developing web servers in some form, and they're really good at just spitting out static content, grabbing something from disk and spitting it out over a network socket. That can be done really quickly these days. So in fact, if you've ever posted to Craigslist, whether for an apartment or for something else, you can, you'll probably, OK, so this side of the room knows. So you'll probably recall that, which now reveals I know this, you'll probably recall that you will be informed that your post will appear eventually, after some number of seconds. And you're given the URL of the admin page where you can edit it. But the listings that we just saw one page ago are not actually updated immediately. So why might that be? Like, why is it? Frankly, it's not the best user experience when sites say, you'll eventually see what you just did, whereas Facebook's pretty damn compelling in that they show you immediately. So why might that be? What's Craigslist probably doing when you post a new advert and they say the listings will be updated shortly? What are they probably doing? Yeah?
It's probably waiting for like a certain number of ads to be posted before updating the page.
Okay, good. So it's probably waiting for some number of ads, maybe 5 more ads to be posted, or for some number of minutes to pass so that there's a cron job, some scheduled process on the server that is then looping through the database, grabbing the newest posts, and updating literally the .html file that represents the listing itself and also the directory listing in the search results. So why would they do this, though? This feels like it's inserting unnecessary latency, especially in 2012. It's faster, right? And frankly, it's 2012, but Craigslist looked like this in like 1999 too. So it is faster. And the upside of that is that they probably do get by with much, much less hardware, certainly than Facebook. I mean, Facebook has tens of thousands of servers these days. I'm guessing Craigslist's technology needs are a little more humble, for better or for worse. So storing things in files, whatever the content actually is actually a compelling thing. And you don't have to store them just on files, on the file system itself. There exist mechanisms that actually streamline this for you. And Memcache Daemon, Memcache D, as mentioned here, is actually an incredibly popular caching engine. In the appliance, if you want to play with this, you can do yum install or sudo yum install memcache D. And what it will do is install a cache server on your appliance that just listens perpetually for connections on TCP port 11211, I think by default. There's no authentication. It's just used for local storage. And then using a few lines of PHP code, anytime you generate a huge string of HTML, you can plop it into Memcache by setting the value for a given key. And what's the key? Well, if it's a user's profile, you might have the key be 123, where that's the user's ID, and then the value is just a huge chunk of HTML. And then in whatever code you've written in PHP or whatever language to request a user's profile, what you do first is you check the cache. And if David's profile is already in the cache, grab that HTML and send that to the browser. Else, if it's not in the cache, or if it's 10 minutes old, a day old, it's probably stale, you can flush the cache, regenerate it by using your normal database queries, save it again in the cache, and then spit out the results. So this is a hugely compelling way of making a website scale without doing a huge overhaul of your architecture. Actually designing things with caching in mind and capturing the output of your PHP files before you spit out the results is a wonderful way of reducing load on databases. Databases tend to be one of the slowest pieces of any web architecture these days, certainly for something like a relational database that's transaction safe and is actually storing with very high reliability all of your data, but you pay the price for that robustness. Anyone know what the MySQL query cache is? This too is a trivial thing to use. And it's not often on by default. Take a guess what it does. That's right. It caches MySQL queries. And all this takes is editing a file that's usually called my.cnf, myconfig, which is somewhere in /etc usually on a Linux server. And if you set the value from 0 to 1, or actually add the line to the config file and then restart the server, what this will do is exactly that. In the future, when you execute SQL queries, the server itself will remember the result set, the rows that were returned, so that if you ask that same query again, it will just return things from the cache. And the database itself will keep track of which data is dirty. For data to be dirty, that means you've written to it, and therefore the cache should be invalidated. The server will do all that for you. So there's some low-hanging fruit here. So especially, and we've experienced this even with the CS50 core shopping tool, where this past fall, things really started to grind to a halt with several hundred users using it all at once, because I hadn't made the best design decisions up front with regard to the table structure and the indices that we had. We didn't have the query cache on. So there was a number of things that in the middle of the night I was able to do without writing a single new line of code, just to get us through that week of shopping period without having to throw everything out, rewrite it, or even add to the server capacity. So realize there's some opportunities here. And then there's other technologies altogether. We can put up things Redis can be used as an object-oriented store for actually storing more hierarchical data than something like Memcache, which relies on strings being the values. And there's many other examples in other architectures for this same idea. Any questions? And again, what's fun is you can, if you care, you can actually play with this stuff on the appliance. And if it is of interest for your student choice of iOS apps, realize you can have a web backend, and you can use the appliance or the cloud or some third-party host altogether for that. So after break, let's come back and chat about some of the database scalability issues and how they relate. And then we'll wrap up with a discussion on these topics. So without further ado, let's solve that database problem. So we introduced earlier in the story a database to actually store state, like our session information. But certainly more generally, if we want to store information about users and profiles and transactions and purchases and the like, we might very well need more than one database. Now, frankly, the simplest solution to scaling your database is often to throw money at it, right? Or throw CPU cycles at it. It's a lot harder, and requires a lot more thought to actually design your databases in such a way that they scale horizontally, though, as opposed to vertically. So here's some of the jargon in the industry. Scaling vertically pretty much means throw money at it. Instead of a gigahertz machine, get a 2 gigahertz machine. Instead of 2 gigs of RAM, get 4 gigs of RAM. And just scale the server up as much as you can. But there's a fundamental problem with vertical scaling based on that definition, which is what? Right. At some point, you will exhaust either your financial resources or the technological availability of hardware. You might max out at 3 gigahertz and 64 gigs of RAM, but there will be some upper limit, whether financial or technological. So thankfully, the world came up with this idea of replication, both in the world of MySQL and relational databases in general, but also in a whole bunch of other contexts. So typically in a web architecture, you will have multiple web servers, and those web servers have duplicate installations of your code. So they all have a /var/www/html directory, or they all have a vhost directory inside of which is your website, and your PHP code and whatnot can be duplicated perfectly across all of those various servers. But the data that changes over time needs to be stored in some kind of database that allows it to read and write and change and delete and so forth. So if the problem is that a single server doesn't actually scale very well, well, you can have this master-slave topology, whereby you have one master server, as you've had thus far, but then you also hang off of it one or more slave databases, as they're called. And their purpose in life is to read data that's being written to the master so that they always have copies of the master. Now, what's the advantage here? In this topology, we have 3 slaves, 1 master. What's the value add then of introducing servers 2, 3, and 4 here? Because they seem to have some fundamentally distinct roles, at least semantically. That would seem to be the case if one's being singled out as master and everything else as slave. Yeah?
The read queries can get divided over 4 servers, only write queries have to go to a single master.
OK, good. So if we leverage that assumption we made earlier, which was that reads are more common than writes, and this is quite often the case, not always, but in the case of Facebook and probably most websites that you've worked on for this class or others, they're probably a little more read-heavy than they are write-heavy. Certainly as they get popular, you get more readers than writers, perhaps. So if that's the case, you could just write your code in such a way that anytime you do an insert or a delete, or more generically, a modification to your database, you send those queries to the master. Whereas if you just want to do a select and some joins, you would do those on any one of the slave databases. So in this sense, you can optimize one server for writes, and then you can triple the amount of capacity you have for reads. So this sounds great, but what are some of the downsides or costs here? Yeah?
Can the slaves be read as they're written to?
Can the slaves be read as they are written to? Good question. Hopefully the database provides us with some form of integrity so that if we do a select while a query is being replicated from master to slave, that we're not going to get part of a row. And indeed, that's one of the things that a transaction-safe database would do, in that you're either going to read the whole row or none of it if you use something like locks or transactions. So in short, we can solve that. Other problems or costs that arise once we introduce slaves 2, 3, and 4 here?
You run into problems of sort of reading before a write has been passed.
Exactly. So what about consistency here, right? Even though you are replicating the data from master to slaves, that's got to take some amount of time, even if it's just milliseconds or microseconds. But in that window of time, suppose that the user has a second browser open, or suppose another user tries to pull up your profile roughly at the same instant you're actually updating it. That begs the question, what are those 2 users going to see? In fact, this too, you can occasionally see symptoms of this on Facebook, whereby you might update something something, and then it doesn't actually appear. And maybe when you reload, it's there, but it doesn't necessarily propagate instantly to that same browser window or another browser window. And that might not be a bug per se. That might simply be propagation delays. And in fact, even though in the ideal world this happens nearly instantly, it can still take several milliseconds, even a few seconds, if all of a sudden you get hammered with a huge number of writes. That might take some time for that buffer to clear and actually propagate to the slaves. There's actually a really interesting Facebook blog post from a couple years ago that I'll try to dig up and post on the lectures page, where they discuss the rollout of their East Coast data center. I believe they started with one main West Coast data center. And then for latency and scalability purposes, they, a few years back, added an East Coast data center. And the idea was to, one, be able to handle more users, but also decrease the number of milliseconds it took for East Coast folks to actually pull up Facebook content. If you have a server on the East Coast and you're on the East Coast, you can assume 10, 20, maybe 30 milliseconds of latency for the round-trip request and response to come back, which is pretty fast. If you're going cross-country, though, it can rise to 70 milliseconds, 100 milliseconds. So you could have that by having an East Coast presence, and never mind the implications for Europe and Asia and the like. So when they did this, though, there was an issue because it was relatively easy, according to their blog post, to just do some replication of slave databases or the equivalent on the East Coast so that you could have much more proximal and quicker reads, so you could access data more quickly. But writes, for technical reasons, were still pushed to the West Coast, as I recall. And I might be flipping the story, but I think this is the direction that things were going in. They still had all of their masters effectively on the West Coast just because it was going to be hard to put masters at the time on both sides, or it was going to require at least more work. So the problem here, though, is that if I'm in harvard.edu and I update my Facebook profile, that update needs to get propagated to the West Coast. But then for performance, they wanted my reads and my reloading of the page and subsequent link clickings to come off of servers on the East Coast. So there was this delay potentially that you would see if things got backed up in the transfer process from West Coast to East Coast. And the article actually talks about some really interesting solutions they came up with, whereby I think one of their solutions was when you do make an update to a page, say your profile page, they would plant a cookie in your browser that would say, hey, I updated something recently. And that cookie would have a lifetime of a few seconds or a few minutes, and that cookie would be used by their own load balancers to decide to keep sending you to the West Coast, at least for a few seconds, so that you see the very latest information, even though it's taking a few more milliseconds to get that round trip there and back. And then once that cookie expires and they assume that the replication has happened, then you get rerouted back to the East Coast. But there are these hoops you have to jump through. And Facebook is certainly not representative of most websites out there, but the number of technological problems that they actually face is really quite fascinating. And I will say, every year they bring out faculty and TAs to Palo Alto to talk about and see some of the technological problems they're working on. And if you do have an interest in scalability, whether it's hardware or software or networking, like Facebook and Twitter and a couple of their counterparts really work on some fascinating scalability problems that are really unprecedented until recent years. So what else is problematic about this besides potential propagation delays? What else can go wrong here? Or what's still wrong here? Yeah.
Will the writes still go to single master? So if that gets too full.
Yeah, so we've kind of just avoided the problem or postponed the problem a little longer, but if our traffic continues to rise, we still have, one, a bottleneck in the form of the master, and we also have a single point of failure, which means if he goes down, we can continue reading, but no one can update their Facebook profiles at all until we get that server back up. Now, one of the compelling features of master-slave relationships is that you can relatively easily promote a slave to master in the event that the master dies, and you could do that automatically with some scripts, or a human could intervene and actually tweak a configuration file, but at least it's a compelling feature whereby if, in the worst case, your master dies and your super fancy write server goes offline, at least within a few seconds or minutes you can promote one of the slaves because it should be a perfect copy thereof. But what else could we do here? Well, this is called master-master replication, and based only on the picture, what problems does this solve? And what problems remain?
You can have multiple masters, so you no longer have the problem of the one master getting too full.
Okay, good. So you have multiple masters, so you no longer have the obvious problem of just one master being full. You no longer have a single point of failure. You have 2 points of failure, but at least probabilistically, that they're both going to die, you would hope, at the same time, is at least a little less likely than just one of them dying. So that seems a plus. But what problems remain? Yeah.
There's still latency.
So there's still some latency. So the arrows from left to right and right to left suggest that in addition to replication from master to slave, master-master replication is also happening here. So in this kind of model, you might very well have another device in the picture, like a load balancer, that decides either via round robin or via load to send inserts and deletes and updates to this guy or to this guy, or maybe always to this guy, but the other guy is always getting copies of them so that he can be promoted if one of them dies. But in short, you introduce some more robustness here, more reliability, but there's also a cost, quite literally financial, right? So it's very easy to just say, well, if we have single points of failure, let's solve the problem by doubling the amount of hardware we have, but this literally has non-trivial implications. As an aside, and as you kind of think about what you might want to do longer term if running your own site, Amazon also has an elastic database service whereby you can create a MySQL topology and have it scale laterally with replication even just by running some commands or clicking some buttons on their website. So you don't need, even though we've drawn things here as pictures, as from this book excerpt, you don't need actual physical hardware. So now let's paint a more complex picture, which is perhaps a little more representative. So at the top we have some client network like the internet. We have the load balancer. We have a whole bunch, 5 of web servers. The arrows then are pointing downward. Let me zoom in if the text is a little small. The arrows are then pointing apparently to a load balancer on the left that then dispatches across MySQL slaves. And then we have one master server on the right that is replicating in turn to the slaves down below. So it's getting complicated, frankly. So it's getting expensive, but we're starting to now combine some of these ideas. But there's still some, there's still some problems here. Find fault with this topology. Yeah, Zach.
Still all the requests are coming to one load balancer.
Yeah.
One point of failure at the top.
Right? It doesn't matter how fancy your internal architecture is, how pretty your network topology picture is, no matter how impressed your boss is, you're still an idiot if you still have, despite all of this effort, a single point of failure that could have been avoided. Now, in fairness, maybe it's a financial decision, and maybe what you do in this case, because this is all you can pull off financially, is maybe you invest in a very expensive load balancer for the very top of the picture, or at least a very expensive support contract, so that if it does go down, the company will replace it within 4 hours, literally on site. So this kind of mitigation is possible. But if you're just doing it and then crossing your fingers, not the best idea. So what would be an obvious refinement here? Okay, yeah. I mean, sometimes it's as simple as that, like multiple load balancers. And indeed, what you can do then is have 2 load balancers that dispatch across those 5 servers. But now we're adding a complication. If we've got 2 load balancers, what's the implication for DNS and for the IP address and all of this? How do I decide which load balancer to send traffic to? RJ?
You could add a load balancer to the load balancer.
You could have a load balancer to the load balancer, and this seems to be kind of a vicious cycle, right? Because then we have a new single point of failure, so we need a second load balancer, but now we have to balance load across these 2. So hopefully there's a solution here. And indeed there is. So there's network level tricks that you can do whereby we could introduce to this picture 2 load balancers side by side, but that have only one IP address. And what you do is configure the 2 servers in such a way that they are highly available. HA is the buzzword here. And what they do is they send heartbeats to one another, which is essentially like a ping from left to right and right to left. And what happens is as soon as one of those servers does not hear the heartbeat from the other, it assumes that he is down, and what the remaining server does is take control of that IP address at a network level. And this is done, if you're familiar, if you took 143, ARP is involved here, ARP, Address Resolution Protocol. The server gets involved and then says, I shall be henceforth IP 1.2.3.4 until this guy is brought back online, and then maybe you can have the IP address back. So you have one IP, but it floats across 2 servers, and they decide dynamically whether or not the other guy is alive. Now, of course, problems here could happen too. Find fault with this story. What else could die in this story, even if it's not pictured on the image?
The network between the
Perfect, right? What are these two load balancers connected to? Well, probably a switch, like something bigger and more expensive than the switch or the home router you have at home, but two Ethernet ports. Now, if those two Ethernet ports are in the same device, you're still an idiot, right? Because you've just now moved the single point of failure from server level to network layer, but this too is bad. So typically in this picture, we would scroll up even higher, and we would actually have two switches in the picture. And you would actually connect this load balancer to this switch, and to this switch with two Ethernet cables, and then this guy would be connected conversely to both of them across both switches. So you really have this mesh effect. And even though this is getting increasingly complicated, these are actually robust engineering solutions to this. But this is why, frankly, services like Amazon's are so increasingly compelling, because my God, like even as your eyes start to glaze over with all of this complexity, it is complex and it's hard to get right and it's expensive, and you need someone 24/7 on site perhaps to actually make sure to respond to all of these things. So a lot of what you get in the so-called cloud is the virtualization of these services. You get the illusion of multiple switches, but there are actually multiple physical switches. You just don't need to know about the actual wirings thereof. But this really is a theme, right? As soon as you see a single point of failure, it's an opportunity to actually improve there. And this picture too doesn't need to be taken literally. We don't necessarily need to buy a new load balancer just to do database replication, database load balancing. It can be the same device, just operating on a different TCP or UDP ports. But this theme of doubling resources is actually quite common in approach. Yeah?
So the MySQL, like the MySQL database, can it store like images or other types of data?
Good question. Can a MySQL database store images and other types of binary data? Yes. You can store them in blob fields, binary large objects. Typically, this is one of these religious things. I would typically say you shouldn't store images in the database, since they're really meant to be storing data, whereas a file system has been optimized over the years for files. And so indeed what you would probably should do is store the paths of files or the file names of files in your database, but then store on disk somewhere on an actual web server or something called a CDN, Content Delivery Network, the actual files. Like Akamai is one, and Facebook has its own now. That just stores static content.
So where would that be in the picture?
So it could be, so for the CDN type services. So if you were hosting it yourself, the CDN would live at the web layer, which is those 5 servers up top there. They're just web servers. But typically CDNs are so intellectually uninteresting that they're typically outsourced to people like LimeWire, one of the two. One of them is P2P, peer-to-peer. Or Akamai or some other services. Amazon has their own as well. And you just get some unique long path. In fact, if you go to Facebook, frankly, later today, pull up any friend's photo, right-click on it, choose copy link location, and then paste it into your browser bar, you'll probably see that it's fbkn.cdn or something like that. It's stored on Facebook CDNs, some of which might be outsourced. All right, how about this one? So partitioning is also a solution, and it actually might be more reasonable, especially since you might think that the previous picture is like many years away from being your problem, perhaps. So what about partitioning, though? Right? And if you were on Facebook very early on, so like in the mid-2000s, what was the URL of what were the URLs of Facebook's of Facebook? It wasn't always www.facebook.com, and it wasn't always www.thefacebook.com. Yeah, so back when it first started, it was harvard.thefacebook.com and mit.thefacebook.com and bu.thefacebook.com. And this is when Mark and company were initially scaling things up, and relatively quickly did one single server not prove sufficient. So what's the quickest overnight change that you can make to scale a website, to roll out some additional school or handle more load? Well, if you had one server originally, right, go to 2 servers, right, and make one called harvard.thefacebook.com and another mit.thefacebook.com, duplicate the database schema on both, duplicate the code on both, and then just use DNS to actually route users to the right one based on, or just tell them, go to harvard.thefacebook.com or mit.thefacebook.com, have them select from a drop-down menu, or based on their login, based on their email address, just redirect them to the appropriate server. And I'm probably oversimplifying the original story, but early on, they did use partitioning. So what does partitioning mean? It means sending some of your users here, some of your other users here, or more generally, putting some data on this server and some data on another server, partitioning it logically based on some rule of thumb. And the rule of thumb in Facebook's early days was if you were a Harvard affiliate, you went on this one. If you were MIT, you went on this one, and so forth. So a picture might look like this. On the left-hand side, you might have a load balancer that sends load across multiple SQL servers, but only for people whose names start with A through M, for instance. And on the right side, you have a replication of that same thing, but for users whose names start with N through Z. And then you have maybe a single master, but the slaves, for reading purposes, are distributed and dedicated to only subsets of your users. So what's nice about this model? What's compelling about partitioning? Yeah?
You have the stuff going to your load balancers immediately.
OK, perfect. So you have the traffic going to one of the load balancers or one set of your servers. It's relatively straightforward to scale, right? If you have twice as many users, just get a second server. And don't worry about the load on a technical level. Just send half of your users to one server and half to the other. What else is compelling here? Anything? Yeah.
I mean, if one of the load balancers went down, half of your users just don't see it.
OK, so we can spin that as a positive. So if half of your servers goes down or one of your load balancers, at least the other half are not affected. Good spin. OK, and conversely, now half of your users are screwed, right? At least in a more generic model, at least an individual user might have 50% probability of having their account inaccessible. But here, all of Harvard would be offline, or all of MIT. Now, maybe that's frankly fine, because this way, at least, the whole demographic is sort of in the same boat, and you don't have some users working, some users not. But that's a design decision. That's a risk you would need to take on. What else is bad about this model? Yeah? Yeah, perfect. Suppose that Harvard or MIT has a much larger user base, and yet you're dedicating essentially the same amount of hardware to each. You can't, or even sort of taking this more logically, if you don't know in advance what the demographics use cases are going to be, you might have spare cycles on one of the clusters, but you can't take advantage of that unless you start special casing certain users on one server or another. Other downsides? That's enough. All right. But this is actually kind of a theme. So partitioning in and of itself doesn't necessarily feel ideal. But if you think about this more generically, this is kind of like a hash function, right? Where you're hashing on a user's name or on the school name. And Harvard users all go left and MIT users all go right, or vice versa, something like that. So in fact, there exist even more sophisticated databases that are truly clustered databases. And if you like this kind of stuff, check out CS165 or 265, which focuses on information and databases. But what you could do in theory is, if one of the problems here is that when you hash on a user's name, they end up on a given server. But if that server goes down, the data is lost or the data is inaccessible. Well, what if you actually had fancier hash algorithm that when you hash on the user's name or the school name, you actually put the data in multiple places? Not every place, but what's better than putting it in one place? Or at least put it in 2 places or 3 places. And indeed, these clustered file system or clustered databases do exactly that. They'll store multiple copies in different places. And some peer-to-peer networks actually do this as well, so that you have redundancy built into the system. And if in the future you're trying to access that same piece of data and you reach a dead end because one server is offline or something's gone wrong, you can at least check the second output of the hash function, which might be the other cluster, looking for that same data. And so I can't emphasize enough, as silly as it seems to just do things twice sometimes, it's an order of magnitude improvement, right? If you go from 1 to 2, you've doubled the potential capacity that you have, the redundancy that you have. And so this is actually a very prevailing theme when designing file systems and databases, to have this built-in redundancy and the ability to dynamically figure out where your data is. Now, how about this? This is a picture that just simplifies the notion of HA, high availability, which generally means just having 2 sort of peer systems talking back and forth by heartbeats or equivalent to make sure that they can each take over the responsibilities of the other. So who really cares about all of this? Well, so when it comes time to actually making your own website, you're probably not going to have to worry about wiring up physical machines, and you're probably not going to actually have to buy a whole amount of hardware. But increasingly, as things are moving into the cloud, you certainly still need to understand these implications for database replication and redundancy, for actually wiring things up for load balancing and the like. And the upside now is that a lot of these same ideas are increasingly implemented in software via nice web GUIs or via command line tools instead of actually having to physically wire things. So even the lessons from CS143 and 165 continue to be relevant, just in a more modern context. And let's take this as an example in just a moment. Yeah?
Yeah, if you have multiple masters, what do you do if you write to the same thing on both masters at the same time?
Good question. If you have multiple masters, what do you do if you write to both masters at the same time? Short answer is you don't. That would be a logic error to actually do that. So you would want to set things up in such a way that the data only gets written to one of those servers. And if you're not doing that, it would be a bug most likely in code or in the configuration. And if you did get it, you'd need some way of, after the fact, cleaning it up, removing duplicates somehow. Actually, I can take that back. You might recall from earlier in the semester or some previous course when you can specify indices indexes on various keys in a database, and you can specify uniqueness constraints and so forth. So in theory, if you did accidentally write a record here and here, but there was some uniqueness constraint, when replication tried to happen, it would not work because it would fail to meet the uniqueness test. So hopefully you would only have one such row in the database. But if the data in the rows is slightly different except for the keys, it's not clear which of them would trump the other. Other questions? So let's take one example here that might relate either to web-based apps or even iOS apps. For instance, I've been, the past 2 or 3 days alone, I've been playing Scramble with friends. And it turns out I really suck at this game. I have lost like all but one of the large N number of games that I played against this. And even one of our former CS50 students challenged me over the weekend via Facebook. And I was like, OK, that's great. I'll play against Vicky, we'll call her. Vicky is amazing at this game. I had like 200 total points. And Scramble's like Boggle, for those unfamiliar. And if unfamiliar with Boggle, not interesting to describe. Vicky blew me out of the water with like 900 points. And so the next round that we played, I handed the phone to one of our TFs who's much better at Scramble than I am. She still beat him. So this is really just a story to say I'm really into Scramble with words lately. And the relevance academically here is that this is an application that talks to a server. So how do you actually implement a game? And please, if you want to win, challenge me at Scramble with words lately. So Scramble with words. And applications like it talk to a server because you have to maintain a history of scores, and you might have a history of chat records. And even more interesting than something like Scramble with words, which only makes occasional connections to the servers, you've got instant messaging clients on phones. You've got the idea of like iMessage now on iPhones, where you can actually see when the other user is typing. And Facebook chat in a web context certainly maintains some kind of illusion of a persistent connection to a server. So this actually gets hard quickly, whereby if you want to make real-time applications, that kind of suggests that your web application or your native iOS application has to have a constant connection to a server. But at least in the case of web browsers, they're not really designed, at least historically, to have persistent connections to servers. It's HTTP, right? This icon's supposed to spin, and then as soon as the web page comes back, the icon stops spinning, and that's it. It's a stateless protocol. So if you want to implement something like a chat program, whereby you can chat in nearly real time with some other user on the network, or play a game against that other person, which needs you to be in constant contact with one another, well, how can you do this? Well, in the world of HTML, what is the simplest, dumbest, but correct way that you could create the illusion of real-time chat in a browser window, whether mobile or desktop? So I type a message to a friend, I hit send. How do I know when they have written back? Yeah. OK, well, that's even too fancy, right? I could just force the user to reload once in a while, or I could do a meta refresh tag, sort of 1990s style, and just reload the whole page. And that's, in fact, how a lot of chat rooms were implemented historically, whereby you might at least have an iframe in there, so you would only reload part of the page, but you just reload it from time to time. But this is not a very nice UI, right? The thing will flash slightly. The scroll bar might get into the wrong position as the content gets long. It's not a very elegant solution. So there is Ajax, where at least every few seconds you could replace a subset of the page's content content a little more seamlessly. But there too, you're going to have a delay. Maybe it's a second. Maybe you're going to refresh every 5 seconds. And it's kind of a crappy chat client if you have to wait at least 5 seconds just to see what the other person says. It's not really real time. But what's the downside of just throttling things up to just checking the server every second? What's that? So something will break, right? So there's only a finite number of connections per second that a typical server can handle. And the problem with the constant connections and reconnections is you're just wasting so many bits and so much time. Besides, if you take 143, you'll talk about TCP and the three-way handshake where 3 messages have to be exchanged just for a TCP connection to get established. Then you have to send these fairly verbose HTTP headers across the wire just to say something like hi. Then the response has to come back from the server, which is similarly bloated. There's a huge amount of overhead involved in using TCP/IP, and you're doing this sometimes literally to send HI. There's a huge number of bytes that are wasted. So that's not the best use. Ideal would be to incur that expense once, send maybe an expensive message or this three-way handshake once, but then maintain a constant connection to the server. But browsers have not historically done this. So there's a few workarounds that people have come up with. So has anyone used or know what long polling is? Yeah, Carl. Okay, so 10 milliseconds. So not quite. So the idea with long polling would be that you do make an AJAX request from client, the browser, to server. But the server actually takes as many as 30 seconds to actually reply. And so what happens is the little icon in the browser will effectively spin, unless it's hidden because it's an AJAX call. And essentially your AJAX request will just sit there almost as though it's blocked, just waiting and waiting as though it's a really, really slow server. Because what's meanwhile happening on the server is there's probably a for loop or a while loop that's executing infinitely, but it's sleeping every second. So it'll execute, sleep for a second, execute, sleep for a second. And every iteration through this loop, it will check the database, or it will check some file on the file system saying, are there new instant messages? And if there are, within that 30-second window, it will finally return an HTML response, which is just HI or something like that, and then the connection will close. But the upside of long polling is that whereas an individual HTTP request typically would take a second, half a second, now these HTTP requests are taking 30 seconds, which is actually good in that you're only incurring the TCP and HTTP overhead once every 30 seconds instead of once every second. Now the downside is you're occupying server resources by sitting there literally in a loop, checking and rechecking the database again and again. But this generally allows you to scale better because you're not wasting time on checking the server again and again in rapid succession. Yeah?
Would that be separate processes for each browser request, or would that be like one batch, like for all new instant messages, like then send them out?
Good question. Would that be one big request for all, one big process or multiple processes? It actually depends on the web server. So something like Apache can be configured with multiple threads or multiple processes. Other servers like Nginx or Lighty can be configured differently. So in short, it depends on the web server. So then there's then you can also use Flash, for instance. So Flash actually has the built-in capabilities to have a socket connection from client to server. But the downside of this is what? Someone answered with the snide remark. Yeah, so it's Flash, right? So which there's a lot of haters of these days. But also, in fairness, it requires actually having the plugin, which even though most people do, it's at least something to be mindful of relying on. So in HTML5, though, there's also something called Websockets, which increasingly is supported, which allows the browser to actually do this and maintain a server-side connection without having to implement this yourself, this sort of poor man's long polling with AJAX. And there's also other server-side solutions. So just to toss out one of the popular buzzwords these days that you see in various startups' email solicitations. So Node.js is actually quite popular. Node.js is a web server written in JavaScript, or rather Node.js allows you to write web servers in JavaScript. So you actually write JavaScript code, but it's executed server-side. And with Node.js, whose threading model is actually a lot lighter weight and more scalable for some things than something like Apache, HTTPD, which comes on most Linux distributions, you can actually handle ever more connections per second by using something like this server side, and then writing JavaScript code using, in this case, a library called socket.io to actually talk to the server. And using something like Node.js, you can actually have a few hundred, a few thousand clients all maintain a persistent connection to the server. And then as soon as the server has something interesting to say, it can trigger an event that everyone then hears. And you yourself, again, don't have to resort to either Flash or this manually implemented long polling. So increasingly, there are, again, a lot of these buzzwords out there. Node.js, Socket.io, MongoDB, Redis, and the like. But they very often do solve well-defined problems. They don't necessarily supplant using more traditional mechanisms like MySQL and Memcache, which have many more years of history behind them. But increasingly, if you're facing some issue related to scalability, do actually read into and read up on how people are using these kinds of technologies, because they actually can solve very well-defined problems. And I would just caution, frankly, from personal experience, simply jumping on the bandwagon of any one of these buzzwords, lest their immaturity and the fact that they are only a couple of years old, a lot of the things that the video snidely mentioned, there's just not as much history behind them if you really want to trust your data long-term to some of these things. So in short, just beware rather than just hopping on bandwagons. Yeah?
Yeah, so you mentioned Node.js is like a server.
Mm-hmm. Mm-hmm.
Does that mean like, Blue Host and stuff like that are Apache won't have that?
Good question. What is the implication for web posts that might typically have Apache? Short answer is it depends. You can spawn a server on any TCP or UDP port, which is just a number. So the only implication there is you could install Node yourself on a commercial web host, a shared account, and you could run it. But it's up to the web host as to whether they will allow TCP traffic to come in on whatever arbitrary port number you chose. So 80 is going to be used by everyone. 443 is used by everyone for SSL. So typically, you would pick a number between 1024 and 65,536 or 35. But that port has to be open. And the gotcha there, frankly, is that if your users are at behind corporate firewalls or on university campuses that themselves block unknown ports, you might be screwing over your users by running something like Node on a non-standard port. However, you can then move to the VPS model, whereby you have full control over the server, and you could run something like Node on port 80 instead of a more traditional web server. And if you still need a traditional web server, then you need 2 servers because of these port issues. Other questions? So fairly complex world, but a lot of interesting ideas. And honestly, if you're interested in like graduate school or interning at not just software companies, but software companies with scalability challenges, there's some really fascinating problems to solve these days when N gets quite large. Yeah?
I don't quite get what the point of Node.js is. Like, what's the advantage?
So short of it is it's a much lighter weight web server. It's event driven, so you wouldn't, for instance, implement this idea of polling by just sitting in a loop and sleeping. Rather, much like the DOM model, client-side in JavaScript, events can get triggered. That's the model that Node implements. So when you want to communicate asynchronously with clients and suddenly, you can just do it much more scalably than using a very heavy server like Apache or IIS in the Windows world, and then on top of that, writing your own custom code. So it's increasingly being used for very lightweight web serving, both of content and also of dynamic messages, like in the case of a chat server. So definitely worth playing with. And frankly, on the appliance, because you can connect from your laptop to the appliance on any port you want, it's a really fun test bed for using any of these things that we've been chatting about today. All right, why don't we adjourn there? I'll stick around for questions. Otherwise, we will see you on Monday for Windows Mobile.